Okay, this is the last lecture, lecture number 5 for chapter 19, and it'll be a fairly short one, but we'll finish it off here. What we can see on this slide here is the natural cycling of the ocean waters. We kind of see, for example, like why is Great Britain, which is way up in the north, so warm? And it happens to be because it's pulling warm water from the south through the equatorial region, and so it keeps it unnaturally warm. Some potential problem is what happens if, say, for example, through global warming, this thermal halide shuts down or changes. Places like Great Britain may not be super thrilled with that, and of course, it could change, currents in other locations and give them different phenomena as well. Other things could be as far as different types of vegetation or parasites and plants and animals that have to change their locations because it may not be hospitable to them anymore. The example we're looking at here, I believe, was with beech trees. Yeah, beech trees. And we're looking at, what is their current range, and that is in this kind of light orangish area. And then if we were to potentially have some type of a global warming, the new range would be somewhere up here. So as an example, right now we live in a beech maple forest location here in Michigan, and according to this prediction, just a prediction, that beech trees would be found much further north than where they are found today. And this goes with a lot of different species. And as I mentioned earlier, basically things can potentially will change. And one thing I mentioned in the lecture before was like malaria. We don't worry about malaria. It's not found up here in these northern latitudes. But in the future, maybe it could be because little plasmodiums with the mosquitoes, they may be able to make their way up here and survive. Something as simple as like fire ants, we don't worry about those up here in the northern climates. But potentially, who knows, maybe they could find their way up here with warmer climate. This is kind of just a little summary of different potential changes that are out there and how likely it is that humans have contributed to this. So if we take a look at all these different trends in here, we see a lot of things that say likely, likely, and certain, and likely again. So you just want to go through some of these on the side over here and say, well, is this going to happen? Is this going to happen? And regardless what the question is, you can pretty much answer it as likely. Okay. Different ways of looking at it. This doesn't say on this slide here, but there's more about reacting to the problem. What do we need to do here? And starting off, we haven't really dealt with it, and I don't think there's any necessary plans on really dealing with it. It's going to be more reaction. But it's not one place's problem. I would say, as far as Americans, United States, kind of started the problem, but it is a global problem now. So we're all going to be kind of dealing with it. So one thing that we potentially could do is something called mitigation, which means we need to stop this. We need to do something to prevent it from getting worse. And we talked earlier that if we were to put the brakes on immediately now, we mostly would be sitting back and waiting for what's out there now to take effect, or just maybe to try to calm down, which will take a long, long time. That's certainly an approach that could and should be taking place, but it hasn't really seemed to be going on. The other one is adaptations. What should we be doing to prepare for this event that is likely to be taking place? So ozone, focus on that really quick. Hopefully we can get through this. We'll try. As we mentioned here, or we're looking at right now, I guess, is the ozone is a great thing up in the stratosphere. It knocks out a lot of the UVC and UVB rays, ultraviolet light. So there's another one called UVA, which passes right on through, and that's what's kind of responsible for giving us our little sunburns. If we end up getting a little bit of the B's coming through, you don't just necessarily get the sunburn, but you can get a lot more of the skin cancer too. Not that the A won't do it. The A certainly can give you skin cancer as well, but the B's are higher energy and can give you a little extra push in that direction. CFCs, chlorinated fluorocarbons, and typically what we're looking at with that, see if I can draw it here. You have a carbon, and typically it has 2 chlorine atoms attached to it, and then you also have 2 fluorine atoms attached to it. That's one of the most common, not the only, but it's probably the most common. Chlorinated fluorocarbons, or chlorofluorocarbons. These things were outlawed a long time ago because they have a lot of negative effects to them. Alright, so here's a little drawing of what's supposed to happen, and see if I can draw this out well. Typically, you have, I'll draw it this way. You have an oxygen molecule, and what happens is some UVC rays, you can see this on the left, come down, and they will hit that, and they'll split it up, and you'll end up with 2 oxygen atoms. Now that oxygen atom will react with an oxygen molecule and create ozone. And then what will happen is that ozone layer will be struck by some UVB, UVC again, and then it just kind of goes back to this beginning stage where you end up with O2 plus oxygen atoms, and the cycle just goes on and on and on. So it's a great cycle that it absorbs all this UVC and UVB coming in from the sun. So we don't get it. So it protects us. The problem is, as I drew on that last page, is you have these chlorinated fluorocarbons, and we're going to focus on just one chlorine atom here for a second. I won't draw on the fluorines. So some UVC comes in and eventually pops off one of these chlorine atoms. So what will happen over here is you have a chlorine atom coming in and striking an ozone, and it breaks it apart. And what you'll end up with is some chlorine with an oxygen attached to it, and then you also end up with some oxygen. And then a secondary reaction happens where you have this chlorine and oxygen combination that'll mix in again with an ozone, and it'll end up with chlorine one more time as an atom, and I'm kind of simplifying this a little bit, with another oxygen. And then coming off there, well actually you end up with 2 of these, 2 oxygens. So ultimately the reaction that you get, this chlorine oxygen is an intermediate, chlorine is a catalyst, and that's a big thing to hear here. The catalyst means you don't need much of it, and it does a lot of damage over a long period of time. So ultimately what you end up with is ozone, as far as an ultimate reaction, turning into oxygen atoms, which bottom line means you don't have ozone. So chlorine atoms themselves do an incredible amount of damage, lessening the amount of ozone out there, and they keep this cycle over and over and over again. So this is just gives a little depiction here as how much ozone loss we've had over a period of time, last 80 years or so. We can see that the numbers have gone down. So last slide on here, a couple of laws that we've had out there. We had the Montreal Protocol that discussed banning some of these substances that deplete the ozone, and we said, all right, well, we're going to eliminate a lot of these. And then lastly, we had the Kyoto Protocol that says, well, yep, we'll get rid of a lot of these chemicals that are depleting the ozone. But the problem is the U.S., you'd think we'd be right on top of things because we're one of the greatest producers of it. We decided not to sign the Kyoto Protocol. And the main reason we said is, well, there's all these developing countries that they don't have to, or they're not signing it. So we don't necessarily have to follow it. We decided not to. But to give us a little bit of credit, have we decreased them? Have we eliminated some of them? Absolutely. But we haven't really gone at it full force as far as trying to limit or prevent the production of them. All right, that's it. That's the end of the lectures for Chapter 19. Done.